Hello all, myself Dr. Vatya Jagan, working as an associate professor in the Department of Electrical and Electronics Engineering, VBIT. So in this video lecture, I am going to explore about the boost converter, which is also called as step-up converter. So if you see my last video where we have discussed about buck converter or buck chopper, which means the output voltage less than the input voltage. And here you can see the configuration of the buck chopper or step down chopper. Right here we can see the power trace converter consists of three elements here: chopper, diode and inductor, and which is performing the DC to DC conversion. So where we are giving the constant DC is the input to the power trace converter, and the output of this power trace converter will be the variable DC. So we have seen in the last video lecture how we got the output voltage, which is a variable one, with the help of the circuit configuration. Now in this video lecture, we are going to discuss about the boost converter. So boost converter is also known as step up converter or step up chopper. So here also you can see the power trace converter block. So this is what our power trace converter. Again, this power trace converter consists of three elements: inductor, diode and chopper. So the input to the power trace converter is a constant DC, here you can see, and the output which will get it as the variable DC. And in case of step up chopper, the output voltage should be more than the input voltage. Whereas in case of step down chopper, the output voltage is less than the input voltage. That is what we have seen, where we have derived the average output voltage is duty cycle times the VDC. And duty cycle is the ratio of T n upon T, and which is always less than 1, which will vary from 0 to maximum of 1. So for any value of duty cycle, you will get the output voltage for a buck chopper is always less than the input voltage. But here in case of step up chopper or boost chopper, we will get the output voltage is more than the input voltage. So we'll derive the expression for that one. So before that, we'll see how this power trace converter is derived. Right, how the boost converter is derived from the buck converter. So if you rotate the elements in the power trace converter in anti-clockwise fashion, then we will get the circuit configuration for boost converter. So now here the chopper has to replace with the inductor. So here you can see this is the inductor, and diode has to replace with the chopper. Here you can find, in place of diode you can find the chopper. Now again this inductor is being replaced with the diode, so you can see the diode here, right? So the position of the element is interchanged and they are rotated in anti-clockwise fashion, so that you can get the circuit configuration for the boost chopper, right? So we'll see how we are getting the output voltage more than the input voltage in case of boost chopper. So let us go for the analysis part. Now you can see this is a circuit configuration which we have derived just now. So where the inductor is connected in series with the battery, so that you cannot get discontinuous input current. Always you can draw the continuous current from the supply, which is one of the drawback of buck chopper, where the chopper is inserted in series with the battery. So when the chopper is in off condition, you will get zero current. some current. When the chopper it is in off condition, you will get zero current. That means in case of buck chopper, it is drawing discontinuous input current. So, but in case of boost chopper or step up chopper, due to presence of this series inductor, we always get the continuous input current. This is one of the advantage of this boost chopper or step up chopper, right? So this is a circuit configuration. Now, I always been telling you that this chopper is always represented with a dotted rectangular box. Why? Because inside this chopper will be having the main SCRs like this. So here we'll be having anode terminal, here we'll be having cathode terminal, and this is our gate terminal. And in addition to this main SCR, we are also having commutation circuit. That is what I am keep on telling you. We'll be having commutation circuit, and the purpose of this commutation circuit is to make the main SCR off. We are not bothering about that commutation circuit, how it was connected. So we are not focusing on that point. But the purpose of that commutation circuit is to make this main SCR off. We'll see how we are going to make off. Right. So, and these are the expected waveforms you may find. Right. Now we'll see how the chopper is operating in mode wise. Okay. Now, if you see the chopper, now this was the chopper equivalent circuit, and here you may find the diode. And I told you that in the inside this chopper, we are having the main SCR like this, right? So this is our gate terminal, and this terminal is our cathode terminal, and this is the anode terminal, right? So let us see whether the chopper is in forward bias condition or not. Because to make the chopper on, the chopper should be in forward bias condition. Here chopper means the thyristor we are focusing, right? So anode is connected to positive terminal of the battery to the inductor. Cathode is connected to negative terminal of the battery. So chopper it is in forward bias condition. I mean to say that SR it is in forward bias condition. So we can make the chopper on, right? But if I make the chopper on, it is replaced by short circuit, you can see, right? So it is replaced by short circuit. At the moment you close this switch, the inductor is charging with this polarity, positive and negative, right? Which means at the moment you close this switch, the negative terminal of the inductor is connected to anode of this diode, and the cathode may be connected to positive. That means the diode it is in reverse bias condition, and it will goes to off state. You can see the diode function here. So which is in forward off condition, it is replaced by open circuit, right? And there is a closed path for the current to flow from source to inductor through chopper and back to the VDC negative, which means this is the current which is charging this inductor. So inductor is charging during this interval. So now if you see the I told you that this is the power transfer converter, and to this converter we are applying a constant DC. You can find the constant DC here, VDC. So these are the pulses which are giving to the SCR. Since the SCR is in forward bias condition, so I apply triggering pulse to the SCR for this much duration. So during T on period, the SCR it is in on condition. So if that is in on condition, we know the equivalent circuit is the equivalent circuit now, where you can find the diode it is in off condition. And since you can see due to open circuit condition of this point, okay, so the load is isolated from the source, so there is no current to the load. If there is no current, you won't get any voltage, so you can find the zero voltage across the load. And since the inductor is connected to the battery, there is a closed path for the current to flow, which means during this T on period, the inductor is charging. So you can see the charge inductor is charging linearly from some I1 to I2 or I1, I minimum to I maximum. These are the steady state waveforms, right? And you can see the diode current, because diode is in reverse bias condition, so it is replaced by open circuit, so you won't get any current to the diode, so diode current equals 0 here, you can see. And the inductor current is also flowing through the chopper, so the charging current of the inductor is same as the chopper current. You can see the chopper current, which is same as this portion, right? So this is regarding mode 1. Now in mode 2 we want to make the chopper off. So as I told you in the previous slide, we'll be having commutation circuit inside this block, right? And due to presence of that commutation circuit, we can make the chopper off, right? We have seen many commutation circuit, right? So before going to make the chopper off, let us see the voltage across the inductor. Now again, one more thing we need to keep in mind, that these diode and the chopper, we consider it as a ideal one, which means there is no voltage drop across them. Why? Because for ideal one, the internal impedance should be 0. Even though it is carrying some current, due to presence of 0 internal impedance, you won't get any voltage across them, right? So now you can apply KVL in this loop. So minus VDC plus VL, it is a voltage across inductor, that equals 0. So if you apply KVL in this loop, so which means VL equal to VDC during on time period, right? So in mode 2, we want to make the chopper off. Forcefully we are going to make the chopper off. So these are the expected waveform you may get during this mode 2. Now with the help of the commutation circuit, we turned off the chopper. So chopper, it is replaced with open circuit. You can see now it won't carry any current to it, right? Because it is an open circuit condition. Now at the moment you off this one, inductor has to release its energy, because previously it has charged to some extent. Now it has to release its energy. So to release its energy, which is there inside the inductor, it has to replace its polarity. So now you can see this negative polarity is replaced with the positive one, and this positive polarity is being replaced with negative one, you can find. That means now the inductor is discharging its energy to the load, right? And as I told you many times, that the current always flows from higher potential to lower potential. So here it is the positive terminal. So now it is again, the inductor is dissipating its energy, or discharging energy to the load like this. So this is one energy you can find, and one more current which is also drawing from the source, right? That means due to presence of this series inductor, you may get more voltage across the load. One is due to presence of the battery, one more is due to presence of inductor. And let us see, there is a closed path for the current you can find. And now if you apply KVL in this loop, as I told you, there is the ideal one. So minus VDC minus VL plus V naught, and that equals 0. This is what you can find, right? And from this one you can write voltage across inductor during off time period. It will be V naught minus VDC. But if you see the voltage, output voltage, simply you can say output voltage from the above equation, you can write it as VL plus VDC, right? So there is a boost in the voltage. Now the output voltage is not only VDC, in addition it is having the inductor voltage as well, right? Let us see the waveforms. So during this portion, I am calling it as a T of duration, where we are not applying triggering pulse to the main SCR, right? And you can see the output voltage across the load during mode 2, which is the summation of VL plus VDC. Now this much is VDC input voltage. In addition to that, you can find this portion, which is a VL, right? And now the inductor is discharging its energy to the load. So discharging current you can find like this. This is linearly discharging, and same current is flowing to the diode as well. So you can see the diode current suddenly goes to some maximum current, then after it will reduce to some minimum value linearly, because inductor is discharging energy. And thyristor, it is in off condition, which is chopper, it is in off condition, so you won't get any current to the chopper. So you can see the zero current to the chopper. And these modes is repeating continuously, right? Mode 1, mode 2, like this. So now you can see during mode 1, this is the voltage across inductor, and during mode 2, you can see the expression for the inductor current here, right? So this is during off time period, and on time period this is during off time period. So if you multiply this with the current and the time duration, you can see this is voltage multiplied by current will give power, that multiplied by time will give energy. That means during on time period, the energy stored in the inductor will be VDC into I into TR. The same current is flowing through here also. So if you multiply this with I and during off time period, that you can say the energy dissipated by the inductor during the off time period, right? In steady state condition, whatever the energy stored by the inductor will be dissipated to the load, right? So now you can see those expression here. Okay. Sorry. If the ripple in the source current is neglected, that means we assume it as a constant one, then the energy stored in the inductor during on time period, just now I told you, that is voltage across inductor is VDC into current, and that is during on time period. So that is the energy stored in the inductor during on time period. Similarly, you can see the energy dissipated by the inductor during off time period. We have seen the voltage across inductor, which is V0 minus VDC. If you multiply that with current and T of time, that will give the energy dissipated by the inductor during off time period. And for lossless converter, whatever the energy stored in the inductor, that should be dissipated or released by it, right? That means we can equate these two equations, right? So if we equate, it will be something like this. So I here will get cancelled, and it will be VDC into T on, that equal V0 minus VDC into T off. So this is what we have derived in the last slide, right? Now I can bring the VDC factor on left hand side. So it is VDC into T on, minus will goes to plus VDC into T off. So I can take VDC common. It is T on plus T off, that equal V0 into T off. So from this equation, you can write, you just cross multiply here. V0 will be VDC into T on plus T off divided by T off. And we know that T, here you can see, T is the summation of on time period plus off time period. Summation of on time period and off time period. So now from this equation, I can write T off equal to, it is T on plus T off, right? From this, I can write T off equal to T minus T on, right? So here, instead of T on plus T off, it is T, and instead of T off, I wrote T minus T on. Now I will divide this equation with T, both in the numerator and denominator, right? So T will get cancelled, it will be 1. T will get cancelled, it will again 1, minus T on by T, we know it is a duty ratio alpha, so you can write here, you can see here. So this is the average output voltage of a boost chopper. Now you can say the average output voltage is equal to VDC upon 1 minus delta. Now what is delta here? Delta is the duty ratio, which is T on by T, which is the ratio of on time period to the total chopping period. Now as I told you, you can get the delta maximum of 1 when T on equal T. That means when there is no off time period, you can say on time period equal to total chopping period, right, which is 1. And you can get a minimum of value 0, which means the chopper always in off condition, there is no on time period. If there is no off time on time period, I can say delta equal to 1. So let us see at these 2 points, what is the output voltage? So these are the extreme points. Now delta equal to 1, if I substitute 1 by 1 minus 1, it is 0 in the denominator. So 1 by 0, it will be infinity, which is not possible practically. Ideally, you can say it is infinity, but it is not practical. Practically, it is not possible. Due to parasitic effects, it is not possible. Right? And you may get the average output voltage 2 to 3 times the input voltage. Right? If you want to get more than matlab 2 to 3 times the input voltage, you need to increase more value of you need to increase the value of inductor, which will be very costly and which will be very bulky, right? So this is the average output voltage, where for any value of delta you may get the average output voltage is always less than the input voltage. When delta equal to 0, if you substitute t 1 by 1 minus 0, it will be VDC, right? So minimum value is, you will get the V naught equal to VDC. So I can write V naught is always less than or equal to V naught is always greater than or equal to VDC. So this is the average output voltage you can see, right? So this is method 1. There is also you can derive the same expression using method 2, right? Same thing. These are the wave circuit configuration. Just now we have seen how it is in on condition, how it is in off condition. If you apply KVL, the voltage across inductor will be something like this. Similarly, in mode 2, this is the equivalent circuit, and we have seen the voltage across inductor is this much, right? So you just apply KVL and just apply volt-second balance principle. So if you apply volt-second balance principle, so during on-time period, the voltage across inductor is this much. During off-time period, the voltage across inductor is this much. You make it is 0, right? So if you make equal to 0, and if you substitute instead of t off, if you substitute t minus t on, right? So you can simplify like this: t on into VDC. Here t off into VDC minus t off into V naught, that equals 0. Okay, and you can take the VDC common from here and here. It will be t minus t on. So this is expression, and now you can cancel. This is t on into VDC minus t on VDC plus t on VDC. So it will be something like this: t into VDC minus t into V naught plus t on into V naught. So you can take V naught common from these two. Here and here you can take V naught common. If you take V naught common, it is t into VDC minus V naught I have taken common, t minus t on. Right, from this one V naught will be t by t minus t on. And we know you just divide this expression both in the numerator and denominator with t. So t by t, it will be 1 here by t and here by t. So you will get output voltage as 1 by 1 minus delta into VDC. So the same voltage expression you can see in the next last slide, right? So this is very easiest way to find out the average output voltage. Method 2 is very easiest method, right? Now we will solve one problem, right? So this is the problem you can see. A step up chopper used to deliver a load voltage of 500 volts from a 220 volts DC source, which means it is stepping up the voltage from 220 to 500 volts. If the blocking period of the thyristor is 80 microsecond, compute the required pulse width. We need to calculate at what value of on-time period you can boost the 220 volts to 500 volts. So that is what we are going to calculate here, right? Now just see the boost configuration, circuit diagram. So we'll be having inductor first, then a chopper. This arrow represents the direction of current. Diode here. You can find the capacitor, right? and thereafter it will be having load here. Roughly I am drawing here, right? And it is battery. Okay, battery is 220 volts, right? And it is required to deliver a load voltage of 500 volts here, right? So at what on time period you can achieve this much of voltage? That is the question, right? Now these are the given parameters. He has given V naught is 500 volts, VDC is 220. T of blocking time period means off time period of the chopper thyristor is 80 microsecond. So we know the average output voltage, which is 1 hour, 1 minute delta into VDC, right? And you can write, let me rub this one, right? So you can write delta is the ratio of on time period to the total chopping period. So if you take T is common, it will be T by T minus TR into VDC, right? And we know T is the summation of on time period and off time period. So here you can see T on plus T off. Here also I can substitute T on plus T off minus T on. T on plus T on minus T on will get cancelled. It will be the average output voltage is T on plus T off by T off into VDC. We know T off, we know VDC, we know average output voltage. Now you can easily calculate what is the on time period. It is 1.6 microsecond. So if the chopping period is on time period is this much, you can get 500 volts from 220 volts DC source, right? So this is the one problem. Okay, even you can find this problem in power times by Dr. MD Singh textbook, right? This is one more problem you can find. Here it is also step up chopper, which has a source voltage of 250 volts in series with a inductance of 0.1 Henry. If the semiconductor switch is operated with the different values of duty ratio, which means the chopper is operating at different values of duty ratio, we need to plot the output voltage versus the duty ratio, right? So we know in case of step up chopper, this is the average output voltage expression, right? So he has to calculate the relation between the output voltage and the duty ratio, right? Now at different values of duty cycle, input voltage is 250 volts. So now you can calculate at the 0.1 duty ratio, you will get this much output voltage. At 0.2 duty ratio, you will get this much. At 0.3, this is what? 0.4, this much. 0.5, this much. 0.6, like this. So you can find in the x-axis, it is at 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. So you can plot like this. The output voltage is on y-axis, input voltage is on x-axis, sorry, duty ratio is on x-axis. So now you can find at 0.1 duty cycle, this is the voltage you can find 277.78 volts. At 0.2 duty ratio, you can find 312.5 volts. At 0.3, you can find 357.15 volts. At 0.4, you can find 416.67 volts. At 0.5, you can see exactly 500, you can see. At 0.6, it is 625 volts. At 0.7, it is 833.33 volts. At 0.9, it is about 250 volts. At 0.9 duty cycle, you can find 2500 volts. At 1, you can get infinity, right? Which is not possible, right? Practically, it is not possible. So this is the second problem you can see in case of the boost converter. So there are many problems are there. You can go through MD Singh and Kanchandani and you can solve those problems. Thank you one and all.